No, Tarzan. No. Okay. So it starts with a picture. And it's a right triangle in the first quadrant. And this picture should look really familiar to you. Say yes, Max. All right, good. We've done a lot with this picture, and we've talked about this angle, theta. We haven't talked too much about this angle up here called alpha. I'm going to use it today, but it's really just a secondary angle. You have a question about alpha?
Why do they use alpha and beta?
Mathematicians like Greek letters for angles. It sort of keeps them out of getting confused with x's and y's and the regular standard.
I know that, but like, why do they?
Oh, why not alpha and beta? Like, why not just start at the beginning?
Yeah.
Okay, so theta is an absolute favorite angle for mathematicians. I'm not quite sure why. Oftentimes, after they've done using theta, they will do alpha and beta. Beta will, like, alpha is their next choice because it's the first of the Greek letters, and then beta is a close second.
What happens when you get back to theta?
I don't think I've ever seen a problem with that many angles.
What symbol is that?
Theta and alpha. Alpha and theta. And that's a 1. That's a number. That comes before 2 and after 0. So, I'm going to take this, and if you remember your right triangle trig, if I have a right triangle and the hypotenuse is 1, the y value is equal to what? No. Say it loud and proud, Peter. Get me out of this mess. Sine of theta. Absolutely. The y value is equal to the sine of whatever theta is. So if theta was 30 degrees, then you could tell me the y value is 1/2. If theta was 60 degrees, then you could tell me that y is root 3 over 2. But if you don't know what theta is, you can't tell me what it is other than saying it's sine theta. Peter, calling someone you did the hard work to tell me what x is equal to.
Sine of alpha.
You're absolutely right. I was hoping you were going to keep it with theta, though. We're going to use alpha a little bit later. You don't mean to say alpha. I know. That's what I knew you meant to say. Cosine of theta. Okay, so those are the x and y coordinates. And I'm actually going to take this whole triangle and I'm going to reflect it into the fourth quadrant. So I'm going to get the same exact thing, except in the fourth quadrant. Is that all right? And, sorry, I apologize if I didn't say this. I thought I was trying to say it. You do not have to frantically write this down or get this derivation. If you want the derivation of this, it's in your book. It's probably online in a bunch of places. You can write it down, and that's totally okay. But more than anything, I want you to agree with what I'm doing or ask me, like, tell me that you don't agree, and I'll try to explain why, because I'm going to get to a result, which is important. Okay? The proof is something that, look, math teachers do because we want you to believe us. We don't want to just put, like, a box up on the board and say, this is true. We want to be able to, like, derive something and have you be like, okay, that's what it means to prove something in math. And every once in a while, we ask you to prove something. Like, actually, today I'm going to ask you to prove some identities. But for the most part, it's more important for you to understand what it is that I'm proving as opposed to how to prove it. And just so you know, I wasn't smart enough to come up with this proof. Like, someone far smarter than I was came up with this proof. The proof of what I want to try to show you is based on the law of sines. And it has to do with this angle here. The sine of, well, what is this big angle? Sine of 2 theta over the side opposite of 2 theta is, so Monty says it's 2y, which is totally true, and we know that y is equal to sine theta. So it's actually equal to 2 sine theta. So the law of sine says the sine of 2 theta over 2 sine theta is equal to, now I'm going to bring in this alpha. sine alpha. And what's opposite sine alpha? If you're looking at this big triangle, 1. Okay?
So, would we put the radius or would we put 1?
In this example, what I'm proving, it's 1. That's where you're looking at a unit circle. Because, Sam, if this was r, then y would be r sine theta, not just sine theta. So that's an important relationship. The only reason y is sine theta is because it's a unit triangle. Okay? Okay, but I can do a little bit better than that because, actually, if you look at this angle, the sine of alpha is equal to, instead of looking at the big triangle, I'm just going to look at the first quadrant triangle. So talk to me. Sine alpha is equal to opposite, which is cosine theta, says Travis, over hypotenuse, which is 1. So sine alpha is equal to cosine theta. As a matter of fact, you probably knew this. In a right triangle, these are complementary angles, right? So the sine of one angle is equal to the cosine of the other. That's why cosine. Co stands for the complementary sine of the angle. So the sine of 30 degrees equals the cosine of 60 degrees. Wait, is that true? Is the sine of 30 degrees equal to... What is the sine of 30 degrees equal to? 1/2? Is that equal to cosine of 60 degrees? Yeah. Oh my gosh, it is. Okay. So instead of writing sine alpha, because I told you I really wasn't that interested in using alpha, I'm going to write cosine theta. And if I cross multiply, I get the sine of 2 theta is equal to 2 sine theta cosine theta. And that is the important result. That's an equivalency. Tell me what you think it says, and then I'll rewrite it. Yep. And I'll even put that in parentheses for you. The sine of 2 theta is equal to 2 sine theta cosine theta. So that's an important relationship, and it's called a double angle relationship or a double angle identity. So you could actually say that the sine of 2 times 30 degrees is equal to 2 sine 30 cosine 30. Now this would be a long way of doing it, but this says the sine of 60 degrees is equal to 2. What's the sine of 30 degrees equal to? You already told me. What's the cosine of 30 degrees equal to? Root 3 over 2. 2 times 1/2 is... So the sine of 60 equals root 3 over 2. But you already knew that, right? So it wasn't that earth-shattering. But this is called a double angle identity. So if you ever want to find the sine of double an angle, it's just equal to 2 times sine of the angle cosine the angle. And we're going to use this when we're proving our trig identities. So that's one important result. Is that all right? I'm going to prove to you another... Actually, let me write down 2 other important results, which you already know, I think. The tangent of an angle is equal to the sine of an angle over the cosine of an angle. Did you know that? Okay, good. And I think something else that you knew. Did you know sine squared of an angle plus the cosine squared of an angle equals 1? I thought you did. A big caution. Many pre-calc students get this sine squared mixed up. Sine squared of an angle is the same as sine of an angle quantity squared. They mean the same thing. It's just a different way of writing it. It's like mathematician shorthand. So if you put the squared by the sine, it's the same as saying sine of theta quantity squared. This is not equal to the sine of theta squared. Because when you write it like that, this is what you're implying. Square the angle and then take the sine. The first 2 are true, and they mean take the sine and then square your answer. Do you understand why people would get confused? And are you going to be one of those people? Good answer, Mo. I love it. All right. Next derivation, and again, you don't have to write. You just have to agree. You have to say, okay, I understand what you're doing, and I'm understanding that. It comes from the law of cosines. So this is why it was helpful to learn the law of sines and law of cosines before we looked at trig identities. So I'm again going to look at the big triangle. And this time I'm going to call this A, B, and C. So I'm going to say A squared plus B squared minus 2AB cosine, what's the angle in between 1 and 1? 2 theta, is equal to C squared. Well, remember Travis and Monty told me what this side was equal to? This whole side's equal to 2 sine theta. So I have to say 2 sine theta quantity squared. All right? Yep, go ahead.
If B is 1
yeah, I don't know. Why did I write B? Is that what you're saying? That was silly. That was totally ridiculous. Thanks, Sam. Say again? We do. And it's going to lead to an interesting result. So we know the law of cosines, and I'm using that with this special triangle that, again, I didn't come up with. I didn't say, you know what would be a great triangle to draw? This wacky triangle that I reflect into the fourth quadrant and get this angle with 2 theta. Someone smarter than I did said this would be a great triangle to use the law of sines and cosines on. And if you do, you're going to get some interesting results. You ready? Ready, Michelle?
I just don't understand people.
Smart people. No, it's look. This is what being a mathematician is about. It's about having these creative, insightful thoughts that lead to learning. It's awesome. Don't get me wrong. It's amazing. Obviously, I'm not a mathematician. I can teach math, but being a mathematician takes a whole different kind of mind. All right. So I'm going to do 1 plus 1. I can do that. 2 minus 2 cosine Evan. 2 theta is equal to, now I have to square this. So I have to square everything. So it's going to be 4 sine squared theta. So I squared the 2 and I squared the sine. I think I'm going to divide everything by 2. All right, that's going to simplify a little bit. You're going to get 1 minus cosine of 2 theta is equal to 2 sine squared of theta. And I'm going to add cosine of 2 theta to both sides, and I'm going to subtract 2 sine squared theta from both sides, and I'm going to end up with cosine of 2 theta is equal to 1 minus 2 sine squared theta. Nope, because I'm going to add cosine to both sides, and I'm going to subtract 2 sine squared from both sides. I did that, Rafi, and then I switched my right and left sides. So I actually did, it was sort of like a double step. You all right with that? Okay. And that's the next result.
What does that mean?
That means that the cosine of a double angle, again, it's a double angle identity, the cosine of twice an angle is equal to 1 minus 2 sine, that does not look like a sine squared, I should write 2 sine squared of an angle. Okay? So, in other words, if you wanted to find out what the cosine of 60 degrees is, 2 times 30 degrees, that would be 1 minus 2 times the sine squared of 30 degrees. So the cosine of 60 would be equal to 1 minus, what's sine of 30 degrees? 1/2. So I have to square 1/2. What do I get? 1/4. 2 times a fourth is? 1 minus a half is? So this is a long roundabout way of saying, hey, the cosine of 60 degrees is 1/2. But you knew that. So that wasn't anything, you had that memorized. That wasn't anything really important to show you, but it's to show you that the cosine of a double angle is equal to 1 minus sine squared an angle. There are, stretching? Yep.
What if the angle stretched across isn't a right triangle?
No. Here's the beauty. This triangle that I drew isn't a right triangle. I was just clever in how I oriented it so that the x-axis goes down this angle to theta. All right? So I could actually take any triangle and do that as long as I split it. So my results are good for any angle, which is sort of nice. Okay, I have 2 more results, and then we're going to start playing our game. All right, so...
Slap it.
Okay, so I have for you so far 1, 2, 3, 4, 5 sort of pieces of the puzzle, and I'm going to add to it a couple more pieces. Do you want to ask? What do you want?
Oh, what's the first one? Sine 2 theta over 2 sine.
Here? Here? Sine 2 theta over 2 sine theta? Just rewrote that. Equals cosine theta over 1. Okay. I'm going to plug in for cosine 2 theta. Instead of writing 1 minus 2 sine squared theta, do you know what sine squared theta is equal to? Peter's got it. Sine squared is equal to 1 minus cosine squared. So instead of writing sine squared, I'm going to write 1 minus cosine squared. And I'm going to distribute, and I'm going to get another result. 1 minus 2 plus 2 cosine squared theta. 1 minus 2 is? Okay, so another way of writing it would be 2 cosine squared theta minus 1. That's just another way of writing cosine of 2 theta. It's an alternate form. Let's see. Is there another way of writing it? There is. There's more. Cosine of 2 theta is equal to 2 cosine squared theta minus, instead of writing 1, guess what 1 is equal to? Sine squared theta plus cosine squared theta. Whee, I ran out of room. I have to distribute, and I get 2 cosine squared theta minus sine squared theta minus cosine squared theta. What's 2 cosine squared theta minus cosine squared theta? Alright, I get cosine squared theta minus sine squared theta. Alright, that completes our interesting way of saying different trigonometric things, and now we can play our game. You getting excited? So, everything I did right so up till now was put into boxes some derivations of interesting relationships. Okay? And these relationships are called double angle identities because we're talking about the sine of twice an angle and the cosine of twice an angle. It happens to be there are 3 different ways of writing the cosine double angle identity. I also wrote for you something we call a Pythagorean identity. Sine squared plus cosine squared equals 1. And this is just a definition of tangent. So I have for you a bunch of pieces of the puzzle. And what we're going to do now is we're going to prove some trig identities. And in order to prove trig identities, these are some of the things I need to know. There might be others down the road. All right? So you ready for the game? Where are my geometry lovers? I know I don't have tons of them, but I know that I have some of them. Do I have some geometry lovers? What, just one? Oh, come on.
I'm not a hater, but
Okay. I appreciate that. You're a non-hater. Okay. If you remember in geometry, we spent some time doing proofs. We spent some time proving things. And actually today what we're going to do are some sort of proofs like that. And if I really had to tell you, for those of you who hate proofs, you are actually doing proofs when you did, like, geometry. Algebra. Sorry. When you subtract... Yeah. State the obvious. What? Yeah.
No, I would leave the end of the test to get 10 points off.
Because it was just that easy? It was easier for everyone?
Do the rest and then...
When you subtract 1 from both sides, you're actually doing a proof. You're just not writing that you're using the subtraction property of equality. You subtracted 1 from both sides. When you divide 2, you just aren't writing that you're using the division property of equality. You're actually doing a proof when you do Algebra 1. You just didn't write, like, the reasons.
It's the reasons.
I still think that way.
All right. It's the reasons. All right. Let me give you a fundamental difference, and then we'll do a few practice proofs. There are two things I can ask you to do. I can ask you to solve the equation 2x minus 1 equals x. And when you're asked to solve something, you're allowed to do things to both sides of the equation, and you're getting an answer. So if I were to do this, I'd do what? 2x minus 2 equals x. Then I'd subtract x from both sides to get x minus 2 equals 0, and then get x equals 2, right? Is that okay? I got an answer, and I did things... I added 2 to both sides of the equation. I did things to both sides, and that's okay because I know that equality is true. That's different from proving. If you want to prove something, this equal sign is like a brick wall. You can do anything you want to the left-hand side. You can do anything you want to the right-hand side. But you can't do the same thing to both sides. Like, I can't add 1 to both sides. Because a proof is asking you a question. A proof is saying, are these two equal? That's different from solving when it's saying these two are equal. If I decided all of a sudden that I wanted to add 1 to both sides, I'm assuming that it is an equality, that the equal sign is true. But I can't assume it because I haven't proved it yet. So when you're asked to prove something, you can do something to the left-hand side. Like, what would you do to the left-hand side? You would. All right? And now you can see that it is equal, and it gets a check mark and a smiley face. Okay? But I can't do something like add 1 or divide by 2 from both sides. Because as soon as you do the same thing to both sides, you're assuming that you know it is equal, and that's violating what we're trying to prove. We're trying to prove that. So you can't assume it if you want to prove it. I know it's a small nuance, but it's important. It's a mathematician sort of thing. Do you get the difference between solving and proving, sort of? Maybe. Yeah. Not really. It's a nuance. It really is. It's a small thing. When we solved, you're allowed to do things to both sides of the equation, like add 1 or subtract 2 or divide. When you prove, you can do anything you want to the right, to the left. You can do anything you want to the right. But you can't do something to both sides of the equation. I can't multiply both sides by 2 until I prove that they're equal. All right, we should do some proofs. Hold on. All right, so I'm looking at your classwork, and I have two different problems, two different kind of instructions. 8A asks me to simplify. And if you take a look at, like, cotangent x times the sine of x, that can be written easier than that. It can be written just in terms of sines or cosines or something like that. And one of the big tricks is to always get things in terms of sine and cosine and see if that helps matters any. So cotangent actually can be rewritten in some simpler form. It's actually, it's not ugly, but we could write it in terms of sine and cosine. Corinne?
Cosine over sine.
All right, cotangent is cosine over sine. And now, when I multiply these, what happens with the sine x's? They reduce, right? Sine x over sine x is 1, and I'm left with cosine of x. So A, you could write it cotangent sine x. A simpler way of doing it is cosine x. Evan.
So, for proofs, since we can't do anything to sides, what if you have, like, one side that's, like...
We're not... Give me a sec. We're going to do another simplification, then we'll do a proof. Okay? And we'll take a look at what strategies work and don't work. All right? No. We'll get there. I have a pretty good idea of what your question might be. All right. Let's take a look at B. And see if we can simplify that. All right, simplifying is sort of like algebra, like we're just trying to rewrite it with fewer terms. So, again, one of the main strategies is try to get everything in terms of just sine and cosine and see if things cancel or reduce or combine. So, I think I can actually rewrite this without using secant or tangent. You have some thoughts or ideas? Elizabeth, and then Evan, and then Monty?
1 over cosine of x.
Okay, so secant is 1 over cosine of x. That's a good start. Evan?
Sine over tangent would be sine x over sine x over cosine x. So
Awesome. Hold on. All right, so that's a great start. So Elizabeth and Evan get us into just sines and cosines. Now I have to do a little bit of algebra. Monty, how do you feel about sine over cosine? Can you tackle that piece?
Reduce it to sine x over cosine x.
Is it sine x over cosine x? Let's think about, there are a couple ways of thinking about it. Instead of dividing by sine over cosine, let's think about it as multiplying. What do you do when you multiply? Flip it. All right, so I'm going to multiply by the reciprocal, so it's the same as multiplying by cosine over sine. So the sine x's, what happens? They reduce. What about the cosines? They reduce. What's this whole thing equal to? All right, now look. I know you might not admit it and raise your hand right now, but there are some of you that actually love this stuff. No, this is simplifying. We're going to get to proofs. But you love when everything cancels out? Yeah. Okay, fine. So maybe you are willing to admit it. It's nice, right? And you wonder, what sort of sick, twisted mathematician came up with B so that this crazy thing simplified to 1? Yeah, like who thought of... It's a game. It's a puzzle. Why do we do crossword puzzles? Right? And this is fun, Rocky. This is okay. It's Sudoku. It's a word jumble. What do you want me to say? All right. All right. We're going to do a proof. You ready, Evan?
yeah.
All right, now, when we do a proof, remember you can do anything you want to the right or the left, but you can't do the same thing to both. So, one of the strategies to think about is, can you simplify the left or right-hand side? And I'm looking at the left-hand side, and I see that there's a lot of simplification we could do. So do you understand why we did a couple simplify problems? Right? We're gearing up. We're warming up. So, I need to take this side and see if I can simplify it and see if that's helpful at all. All right? Peter, thought or idea?
Well, cosine x and secant x is 1.
All right, because secant x is 1 over cosine x, right?
And then
Hold on. So, notice with my proof, I'm working myself down, and I'm asking myself a question. Can I prove that these two are equal? Cosine times 1 over cosine is 1 cosine squared x. And I'm asking myself, is 1 minus cosine squared x equal to sine squared x? And some people might actually see it right away. And they might be willing to say, yes, it definitely is. Because it's plus cosine. Right. Now, in order to do that, we would have to actually add cosine squared x to both sides to see sine squared x plus cosine squared x equals 1. But we can't add to both sides. So, a way around it, and you might think it's like a silly last step, because you don't really have to, you could actually work on sine squared, and we know that sine squared is equal to 1 minus cosine squared, because sine squared x plus cosine squared x equals 1. So what's sine?
I mean, do we really have to do that if we know? Because if we know that, don't we know that it's going to last?
All right, so an alternate last step, Elizabeth, could have been, hey, I know that 1 minus cosine squared x is equal to sine squared x. Okay, that's an alternate last step. But either way, you need to show that the left-hand side is equal to the right-hand side, or the right-hand side is equal to the left-hand side. It now gets a check mark and a smiley face. Mo?
And the way you prove that, like last step you did, is that an equation?
Yeah, I knew this, right? I knew this Pythagorean identity, and it was because it was one of the boxes that we talked about. And so if I know this Pythagorean identity is true, then I know that either 1 minus cosine squared equals sine squared, or as a result of this Pythagorean identity, I know sine squared equals 1 minus cosine squared. So either of them would be all right. Evan, then Elizabeth.
Just to wraps up my other question, original question. So do they have to be in the same exact form?
Yes. Like when you get to the last step?
Yeah.
Yeah. You want them to look exactly the same in your last step. It's almost like when you did proofs in geometry, you knew the first step was going to be given, or the last step was going to be what you're trying to prove. Your last step has to be, it has to be the right side equals the left side. Now, I don't know if this is your question, but I'm going to say it. In a more complicated problem, you might actually change the right-hand side. It might look different. And you might change the left-hand side, and it might look different. But your last step has to be, those two different things have to be the same. So it doesn't have to be what you started off with, but it has to be exactly the same as the other side.
So if we're dealing with like numerical values,
not going to happen. Nope. Elizabeth.
So like, are we gonna say like for the reasons, like for that one, we just say, like,
You don't have to write the reasons. Yep. There are no reasons to write. Okay? That made it all the difference in the world?
Yeah, pretty much.
Sweet. My day has been made because Monty just said he's now officially a pre-calc fan. Alright. This is C. We're going to take a look at one more and see what we can get in. So, here's the thing. When you're doing these proofs, usually oftentimes there's a more complicated side and a less complicated side. Most of the time, if you simplify the more complicated side, you'll see that you either have the other side or you're really close to it. So, top strategy, try to get everything in terms of sine and cosine. You okay? Drink? You sure? Okay. Cosecant is 1 over sine. Secant is 1 over cosine. Cotangent is cosine over sine. Now, I'll admit, does anyone feel like that left side just got a lot messier? I don't know if that's any better. Let's do a little bit of work. Instead of dividing by 1 over cosine, dividing is the same as doing what? Multiplying by reciprocal. So I have to multiply this whole top by cosine. And let's hope that something nice happens. or something nicer happens. Okay, so I have to distribute. I get cosine x plus cosine x over sine x minus cosine x over sine x is equal to cosine x. Now, I could definitely rewrite cosine x over sine x as cotangent x, but if I have cosine x over sine x and I minus cosine x over sine x, that's 0. What am I left with on the left side? And that is exactly what's equal to...
I like that. I really didn't like writing that.
No, we didn't solve. We proved that the right hand was equal to the left hand because we simplified each side. We didn't do anything like add 1 to both sides or divide 2 by both sides. We just worked with one side at a time. As they get more complicated, it's not going to be just one side that needs simplifying. You're going to need to do it on both sides. But I heard many people admit that they liked this. So I'm going to leave it at that. Mr. Evan.
Will we in this chapter have to deal with proofs that are like